you had a nice evening yesterday in beautiful weather in Montreal. So we are going to start the sessions today with the initialization session. I'm Barbara Casati, I'm going to chair the session. And the first speaker of this session is Thomas Collo. He's going to talk about an overview of the CPC CIS initialization system and its use in experimental CIS forecasting at the NOAA Climate Prediction Centers. To you.
Okay, thank you very much. So I'm excited to, start off another day of talks at the workshop. So I'm talking about our new CPC CIS initialization system that we've developed at the NOAA Climate Prediction Center. So these are my collaborators, Drs. Wanshu Wang and Arun Kumar. So outline of my presentation, first I'll go through a brief history of our experimental CIS forecasting at the Climate Prediction Center. Then I'll talk about a rationale for developing a new CIS reanalysis system, followed by an overview of the workflow involved in developing the system. Then we'll test the CIS assimilation out, and we'll take a look at CSIS, the use of it in a coupled forecast model, and then I will conclude with an early forecast for September 2018 CIS conditions. So history and motivation. So I think some of you in this audience might be familiar with the work that we are doing with PyMOS CIS thickness and initializing it within the climate forecast system version 2 model. So basically why we are doing it is because when we use the operational climate forecast system version 2, which is initialized with CIS thickness conditions from the climate forecast system reanalysis, CFSR, it does not capture the seasonal cycle, internal variability, or the long-term trend of sea ice. You can see it's well above the observed. But then when we use an experimental version of the model with sea ice thickness from PyMOS, we can see trends and variability much more in line with the NSIDC observations. So as a result, starting in 2015, we started issuing experimental sea ice forecasts to the National Weather Service Alaska region using this experimental system. So if everything is working well using the PyMOS initialization, the question becomes, why are we interested in developing our own sea ice reanalysis system? So the first factor is forecast model consistency. So CFS uses the Geophysical Fluid Dynamics Laboratory Modular Ocean Model for the ocean, and PyMOS uses the Parallel Ocean Program. So PyMOS, the sea ice model in PyMOS has actually 12 different thickness layers for sea ice, whereas for CFS version 2, there's only 5 layers. So in order to ingest PyMOS data into CFS, some level of interpolation needs to be done. So by using the same ocean model for the initialization system that is used in the coupled forecast model, we can eliminate that middle step. So the second idea is to remove dependency on an external source to improve operational reliability. So PyMOS data comes to us from the University of Washington. So that means that we need to depend on an outside source for data that we need for a real-time operational product. So if we can develop the product ourselves in-house, we can eliminate the need to depend on the outside data source. So finally, we have a better representation of sea ice concentration and thickness through data assimilation. So both PyMOS and our product assimilate sea ice concentration, but not sea ice thickness. I think plans to test sea ice thickness assimilation are planned for the future. So if we just take a look at sea ice extent, do a comparison between the CFSR product and NASA team observations, you can see this is for the month of July. You can see starting at about 2006, there's quite a bit of divergence between CFSR and the NASA team product. And looking at this for all months and all years from 1992 to 2016, you can see, well, there's two very clear changes in the differences. This is actually due to different sea ice initializations being used in the CFSR product. But overall, you can again see that after about 2008, For the period between, say, February and August, sea ice is much greater in CFSR than it is in the NASA team product. And if we look at sea ice thickness, again, CFSR, very high sea ice thicknesses across the Beaufort Sea, into the Chukchi Sea, and across the Central Arctic Ocean, that is not seen in PyAMOS or in the remote sensing product. In this case, it is from the VIRUS product. You can see PyAMOS and VIRUS are rather similar, with CFSR having too much sea ice. So these are two factors we would like to improve in our new initialization product. So how does this work? How are we building what is the workflow for our new product? So essentially we use the BOM ocean model, and we started on January 1st, 2005, and we treat the first year as a spin up, so we start saving our data on January 1st, 2006. So we'll start our run at 0Z. We ingest sea ice concentration from NASA team. After about 2017, we use the near real-time data set. So we also ingest sea surface temperature data from NCEI, and we have a restart file, and the restart file contains ocean and ice initial conditions. So after we ingest all three of those data sets, we run the model forward for 24 hours, and we stop on 0Z the next day, at which time we produce a new restart file. So then we repeat the process with the new restart file, ingesting restart files, surface temperatures, and sea ice concentration. And then it's also this restart file that becomes a set of initial conditions for our coupled model for sea ice hindcasts and forecasts. So a quick overview of how we are assimilating sea ice concentration. It is a simple nudging procedure first developed by Lindsay and Zhang in 2006. So basically, the assimilation factor is related to a weighting factor, and we can choose to weight the model more so toward the observations or more so toward the model. So in this case, so the weighting factor in this equation is a function of this parameter alpha, where for small values of alpha, we are weighting more toward the observations, and for large values of alpha, we are weighting more toward the model. So for the CSIS data set, we decided to set alpha equal to 1. So we are actually giving the most weight to the observations. So you can see on this plot for alpha, value of alpha equals 1, the teal line. So even for small sea ice concentration differences between the observed and model, the weighting factor is large, and the actual nudging value is nearly linear, versus had we chosen a high value of alpha, say alpha equals 9, this would indicate that even if you had CS concentration differences up to 40%, there would be no nudging. So we wanted to give the most weight to the observation, so that's why we chose the small value of alpha. So initial testing of the seasonal cycle produced by CSIS. So on the left is showing mean Arctic sea ice extent over the 10-year period from 2007 to 2016. And on the right, we are showing Arctic sea ice volume over the same period. So for CFSR and CSIS, so we did 2 runs of CSIS. One with the assimilation of sea ice, and then we did another run in which we did not assimilate sea ice. So for CFSR data and CSIS, you can see throughout the year, sea ice extent and sea ice volume are both too high, whereas if we assimilate sea ice with CSIS, it is much more comparable to PyAMOS and the observed. Actually, PyAMOS has a too low sea ice extent in the winter, which is corrected in CSIS. So it's hard to tell between the black line and the blue line, but they're nearly identical. That's why you can't really see them throughout the summer, because they pretty much overlap each other. All right, so another factor to consider is the representation of sea ice over the Bering Strait. So this is for December mean sea ice concentration from 2007 to 2016. So if we look at CFSR data, sea ice concentration is slightly too high by about an order of 10 to 15%. In PyAMOS, this bias is nearly eliminated. So with CSIS, with the run that no ice is assimilated, we get this very large negative bias in sea ice concentration over the Bering Sea. But we eliminate that bias when we assimilate sea ice, and we make the product more comparable to biomass. All right, so with the CSIS product with assimilated ice, we've decided to do hindcast, in which we initialized a coupled CFS model. So for this experiment, we initialized on June 21st for the years 2012 to 2016. And this is the 5-year mean seasonal cycle of sea ice extent. So we initialize with the CSIS initial conditions, the biomass initial conditions, and also CFSR initial conditions. And the black line represents observations from NSIDC. So you can see CFSR, again, as we talked about at the beginning of the presentation, produces too high sea ice extent in September with comparable values from biomass and CSIS. So looking at the year-to-year variability, again, the same patterns are relevant. CFSR initialization produces too much sea ice extent in September, whereas the CSIS and biomass are much more comparable to each other. And of note here, this first year is actually 2012, so it would make sense. This was a record low ice year, so it would make sense that these would be the lowest values of the data set. And if we look down here, we look at the September mean sea ice concentration. So with CFSR, you can see very high biases in sea ice concentration across the Arctic. And with biomass initialization, you can see very comparable to CSIS. Still a bit of a high bias here over the Beaufort Sea in both data sets. That's, I think, something that would have to be investigated later, but otherwise both products are very comparable. So quick summary, experimental sea ice outlooks have greatly benefited from the use of initial sea ice conditions from biomass. Improvements exist in the seasonal cycle and year-to-year variability. So we decided to create an in-house product at CPC, namely the CPC sea ice initialization system. And it's done because we want to maintain consistency with the forecast model, remove dependency on an outside source, and also improve on current reanalysis systems. And the CSIS product produces similar results in terms of the seasonal cycle and interannual scale as biomass, and is substantially improved over CFSR. So starting in 2018, CSIS is now being used to initialize CPC's experimental seasonal sea ice forecasts, as well as week 3 for sea ice forecasts that are being done by my colleague, Dr. Yanyan Liu, also at CPC. So how are we doing on time?
Actually, you have 7 minutes.
Okay.
5 plus 2.
Okay. So I'll go through my September 2018 early sea ice forecast based on the CSIS initialization system. So this is based on initial conditions in the model starting on April 21st through 25th, 2018, is based on 20 ensemble members, and we use a 11-year hindcast data set, also initialized April 21st to 25th, to correct systematic biases in the coupled model. So for 2018 sea ice extent forecast, we can see our predicted value is 4.5 million square kilometers with an error of about 0.29 million square kilometers. So that puts us in the range of about 4.21 to 4.79 million square kilometers. So that would be on the low side of the 2009 to 2017 median, but it would not be a record low year. And I think we are somewhat confident in this forecast. So I did the looked at sea ice area, and these are different regions that were used. So I'm not going to go through them, but and this is sea ice concentration for September 2018, produced by the 20-member ensemble mean bias-corrected data set. So pretty much in all of the regions, our model is predicting low sea ice area, except for the Beaufort Chukchi Sea, which I found pretty interesting. It's a pretty high prediction. So I know we saw some other talks yesterday that would also, I think, support a greater area of sea ice in this region. So, okay. Thank you.
Thank you very much. Thank you very much. Questions? I have a quick one.
Just out of curiosity, what is your estimate for the errors before correction?
For this September sea ice,
Correct.
the error, which was determined by ensemble variability, was 0.29 million square kilometers.
Okay, thank you.
No problem.
You mentioned that when you do your nudging, you do it with a alpha equals 1 parameter. So you do a very hard nudging of the analyzed sea ice concentration. But if I understood correctly, the analyzed observation product you're using is just a passive microwave product. So wouldn't you expect then there to be saturation issues at high concentrations? And my question was then, do you do anything special to account for leads in the pack ice?
So far, we haven't actually investigated that yet. I don't know if the resolution of the data we are assimilating would be actually enough to capture sea ice leads.
Because it might be something to look at. I noticed when we were doing similar things that you can get values around 97%, 100%, and whereas in the observed analysis, it'll always be 100%, and so you can end up basically filling in leads in the model ice cover.
Okay. Yeah, right. Yeah, our horizontal resolution, I think it's about half a degree. So I think we actually might be missing some of those features.
Fred?
So regarding Greg's presentation yesterday, how do you project the on the different categories the ice concentration increment?
Oh, sorry, I forgot to go over that. So when we nudge sea ice concentration, we start with the lowest thickness category and work our way up. So the lowest thickness category in CFSR, I believe, is 0 to 0.1, and 0.1 to 0.3 meters, and 0.3 to 0.7 meters, and so forth. So we start with that lowest category, and if we still need to nudge, we work our way up to the next highest category. And then for points where we need to add sea ice, and that based on the nudging, and there was previously no sea ice, we assign an initial sea ice thickness of 30 centimeters.
Very good. Any other question? We're good. I think we move on. Thank you very much again. So the next presenter is Ed Blockey. He's sipping some water. So he's going to talk about improved seasonal forecast of summer sea ice extent using the simulation of the cryosat thickness. Be careful of the edge. So I'm going to signal when you have 5 minutes questions. Time.
Thank you. Okay, so I'm going to talk a bit about motivations for sea ice thickness initialization. And I should say before I start, this is work I've been doing with Drew Peterson at the Met Office, and it's been funded under the EU Applicate project, partially. So the main motivation is really that a lot of these large-scale dynamical systems are assimilating sea ice concentration, fairly commonplace at the moment, but thickness is not. And there have been several studies, which I'm not going to go through, that have suggested that thickness is a very important indicator, predictor for summer extent. And we now have Cryosat 2 data available since 2010, so I'm going to take advantage of that. And my main question really here in red is how will using the sea ice thickness initialization affect our seasonal forecasts with Glossy of Arctic summer extent? And what are the relationships between the spring thickness errors and the concentration errors? And I have some secondary questions, which are mainly just about, does it work? Can we get it into the model properly? So very briefly, tell you about our seasonal forecasting system. It's called GLOSY, which is a very clever acronym, first three letters of global and seasonal. And we're using NEMO and SICE ocean sea ice models with our unified model atmosphere. And this runs every day. We do two 210-day forecasts and a series of monthly forecasts and hindcasts. The main point is that we initialize this from our ocean and sea ice analysis system foam, and we are simulating in that sea level anomaly, sea surface temperature, profiles of temperature and salinity, and passive microwave sea ice concentration, all using 3D VAR system, but we don't simulate thickness. And these are just a crude schematic to show what we currently have. We have atmosphere model at the moment doing its thing, atmospheric analysis. We have the ocean and ice model, an ocean ice analysis, and we basically just stick those together. Oh, will do. You stick those together to create our seasonal forecast. So I'm just going to talk a bit about what I've done with the ice thickness. I've taken the Cryosat 2 product from CPOM in UK, and I've performed a nudging. So I'm still doing the 3D VAR data simulation of everything else, but I'm nudging the thickness to Cryosat data with a 5-day relaxation timescale. So I'm just trying to force the model to look more like Cryosat 2. And I'm not worried too much about the errors in Cryosat 2. I just want to know whether it makes a difference. And it does. So in our reanalysis system, hope this has come out okay, but this is 1st of May. So after adding the Cryosat simulation all winter, we find we have a lot more thicker ice here in the Atlantic section and a lot less in the Pacific. So what does this mean for seasonal forecasts? So I've run a glossy ensemble of forecasts, 24 members per year, from early May, late April, through to September for 2011 to 2015. And as I should say, this is a prototype version of glossy, which is currently being tested for operational implementation. And here are some results for 2011 and 12. On the left, we have the control glossy, and on the right is my thickness glossy. Blue here is probability of ice, so the number of ensemble members with ice, where ice is concentration above 15%. And the orange, so the orange here is the ensemble mean ice edge, and the black is the observed ice edge from the OSISAF product. So I was very pleased to see that this has made considerable, and also this happens 2014 and 15 as well here. So I was very pleased to see that this has made quite a significant difference, and the model now looks a lot more like the observations, particularly here, 2015, and 2012 looks pretty good as well. So I was very pleased about that. Total extent has increased. So here the pink is my thickness data simulation run, the blue was the control. Ignore the fact here that those are different, but the NSIDC and the HADIST and OSISAF data are all pretty similar for the period that I'm looking at. However, as many people know, basin-wide extent is not a very good metric, as Greg's canoe cartoon illustrated yesterday. So I've been looking at Helga's integrated ice edge error diagnostic, which is the integral of basically all of the erroneous areas of the model where you've either predicted ice that wasn't or vice versa. And again, here the blue is the control, and the pink is my thickness data simulation run. And there's a 37% reduction here in ice edge error, which is very nice. And it's not surprising given when you see the spatial plots, how much more similar they were to the observations. So I want to talk a little bit about the importance of those initial conditions, because as I noted before, this is 2012 as an example, the assimilation is increasing the thickness of the ice here, and it's decreasing the thickness here. And at the same time, we have a situation where, so here the pink is with the thickness assimilation, the black is the observation. This area is much better simulated with thickness, whereas previously our extent was kind of spread around here where the ice was too thick. So there's clearly a very strong relationship between the thickness errors in the model, climatology, and the end result. So I've been asking the question, does it actually matter that I'm using the correct year, or am I just really fixing the model climatology? And to try and answer this, I reran the whole experiment 2 more times, actually, one using 2015 initial conditions every year, once using just the sea ice, and once using ocean and sea ice for 2015. And here are the results. This is Arctic extent. And you can see that this is the control again. This time the green is the result with the same initial condition. And the main thing I note here is that the green line is incredibly flat, which I hope means that our ensemble is large enough to deal with the atmospheric noise. But I think also means that the initial ice volume does exert quite a control over the eventual extent that we have. And I haven't included it here, but the run with the ocean as well also wasn't this flat. So the ocean is not having as much of an impact as I thought. I was a bit surprised. So, important point down here. Only a 5-year, or 4-year, because 2015, of course, is the same. So I've not been able to show, actually, that the pink line is significantly better than the green line. Whereas previously, the others were significantly different. So in summary, I've highlighted that the thickness here is at least promising. It works. It is fixing biases in our model, particularly here in the Atlantic sector. However, has revealed that the model bias is a bit of a bias in the model thickness distribution, which we need to fix. And the suggestion is actually that this is likely higher order concern than the simulation of thickness. So what are our next steps? To look at various things to try and improve the thickness distribution, including we are currently doing some work with the EAP rheology insights and the form drag scheme. And there's also looking at the ice strength, as was mentioned yesterday by Greg, I think, that the, actually it was Jean-Francois, sorry, that using the HIPAA scheme can maybe give better results. And we do have a post now that's looking at implementation of thickness within our 3D VAR system. So that's about all about the thickness. I've just got a little bit about our forecast for this year. Well, I have 2 forecasts. So I sent one in as soon as Charles emailed us all, which was this one. So 4.4 plus or minus 0.9 million square kilometers is our forecast from early April. And this is low, and I've put somewhat uncertain, given that the plus or minus 0.9 does actually take it between record low and almost into high. And this is the P-ice, probability of ice plot here, and I've had a crack at what I thought the northern sea route, the northern passages would be like, low for the northern sea route. However, I mean, we do these every day, right? We run the model forecast every day. So we have one from towards the end of April. Drew is now experimenting with a nicer figure, and so it's slightly different. But this is the P-ice. You can see if I flick back and forwards, actually there's quite a difference here in the Northwest Passage. So our updated forecast is 4.1 million. This is still low and somewhat uncertain, but the Northern Sea route is now high. So I guess that's uncertain as well. Thank you very much. And one thing I should say is that apart from the forecast, all this stuff is available currently in the Cryosphere discussions paper. So please feel free to have a look and try not to leave any horrible comments. So thank you very much.
One question, yeah.
So the new ice depths, as for the recent years, how about in your hindcast? Because I mean, in the real-time forecast, you can use this.
Yeah.
But in the hindcast, you don't have the same ice thickness. So you correct the bias, but it hurts the scale.
Yeah, that's a good point. So what we are hoping to do with the reanalysis is to use much more than just cryosat, and to use ISAT, and to use Envisat, ERS 1, 2, you know, all the stuff that's available. However, most of them don't go that as far north. So as you say, clearly fixing the model bias is important as well. So that's what my group are working on at the moment.
Yeah, in the thickness DA experiments, it seemed like the prediction results looked quite promising for every year, with the exception of the high event in 2013, where you had a low sea ice extent in that year. So any thoughts on what went wrong in that case?
Yeah, I've called this my black sheep. I didn't have time to include this slide. So I don't know what went wrong. So there's some of the individual members, they look a bit crazy. So basically we didn't capture this, was what was wrong. But some of the ensemble members do. I mean, this one looks a bit mad. I've had a little look and I've not really been able to say. I was rather hoping that 2013 might have been a more difficult year to predict, because it's quite random, but I don't know. There has been a suggestion that maybe the snow cover was particularly high in the winter before, and so maybe the cryosat data was not so good because they just used the climatological snow, the Warren snow, I think.
Hi, Ed. Out of curiosity, you say that it reveals persistent bias in the model, too thin ice in Eurasian Basin and too thick ice in the Beaufort Sea. Mm-hmm. Do you have any thought about the reasons of these biases?
Yes. So, next step. So, we think it's dynamics. We think it's dynamics. And so what we are looking at rheology and momentum drag. So we think the ice is just moving too far around the Beaufort dry, and the impact is too far. Sorry, we think it's dynamics.
Even in the Eurasian Basin?
Well, we think that the ice is just circulating too far around. Maybe there's too much divergence. I don't know. We haven't looked in thorough detail, but we do have do have a very high momentum drag actually that the land people put in because it gave them better surface pressure biases.
Will you try to change the ellipse aspect ratio like Miller did? Like he corrected his bias from a very similar bias using a higher aspect ratio, and Amélie here also was suggesting that maybe like a higher aspect ratio with the ellipse would be a better fit with the RGPS deformation.
Yeah, so what we're doing at the moment, and Keen in my group, is looking at the EAP rheology, but we have additional plans to look at maybe some changes like that to the aspect ratio, but also the ice strength parameterization, maybe using the Hibbler scheme. So we're looking at multiple different things at the moment, but focused on dynamics.
I would include just the standard ellipse with a different aspect ratio. The EAP is a new rheology, and it's still unclear like how it's all working out. So it would be good to work in step, I think. Yeah, just for the community, I think.
I think there was another question from Bill.
Right, yeah, just referring to your last slide, I was just wondering how you define the ice edge based on an ensemble forecast?
So here, this ice edge is the ensemble mean 15% ice contour.
Okay, but not the contour of the ensemble mean, but the ensemble mean of the contour, because it does make a difference.
It is the contour of the ensemble mean.
Okay. Yeah, because of that threshold, I think you may tend to get a larger ice extent based on the ensemble mean than taking the ensemble mean of the ice extents, because the ice edge will be different, and you may have more than 15% here, more than 15% there in different ensemble members, and when you average, when you take the average concentration, it sort of takes the envelope of that. But
so that's just those pictures. For these plots, this is the mean of the extent.
Right. Yeah.
But for the 2D depiction of ice edge, it was much easier to do the other.
Yes. Okay. Thanks. Just another possibility is to define it as the median of the sea ice probability. So that gives you a 50% probability. So anyway.
Yeah.
Very good. So thank you very much again. So the next talk is Bill Merrifield. He's going to talk about the importance of temporal consistency for sea ice initialization in seasonal forecasts, so what they've learned from CANSIP.
Good morning, everyone. So this will be about efforts to improve sea ice initialization in a third operational system, which is the Canadian system, CANSIPS, which stands for Canadian Seasonal to Interannual Prediction System. So the current version of CANSIPS has been around for a while. It's based on two versions of the CCCMA global climate model, which have different atmospheric components and the same ocean and sea ice components. So they have 10 ensemble members each and run for 12 months from the start of every month. So with respect to sea ice, the sea ice model is very simple, 2.8 degrees, which is the atmospheric resolution, which is very coarse by modern standards, single thickness category, and uses Flato-Hippler cavitating fluid rheology. To initialize, and yeah, I should just mention it was one of the first forecast systems when it came online in 2011 that has interactive sea ice. So the model is initialized by bringing in data constraints in coupled runs of the model. So the blue here represents these assimilating runs which provide initial conditions for the forecasts, which are green here. And so these data constraints are on the atmospheric variables, SST, and sea ice concentration. For sea ice concentration, we nudge to the HAD ISST1 analysis in the hindcasts, and in real time, we use the 3D VAR sea ice analysis, which is used for weather prediction. Sea ice thickness, on the other hand, is from a seasonally varying model-based climatology, which back in 2011, 2010 sort of is what we had on hand. And these seem like reasonable choices at the time. First three papers, I believe, describing efforts to forecast sea ice using a global climate model all came out rather close to each other. There's this one based on the Canadian system, this one based on NCEP, and this one based on the French model. And so these were very early days for sea ice forecasting. And as far as I know, these efforts really, although around the same time, were pretty much independent of each other. So it was interesting to compare the results of our system with those from NCEP and the French system. And so these plots of anomaly correlation as a function of predicted month and lead time, perhaps coincidentally, are rather similarly formatted. And so we see from the full values and the detrended values rather similar patterns between Canadian and American systems, where the hatching and dots represent statistical significance. Overall, I think the NCEP skills were a bit higher, but given the sort of relatively simple initialization of sea ice and the coarseness of the model and the simplicity of the model, we felt reasonably good about that. So clearly there is skill in the hindcasts. And so from the CNRM CM5 model, there were values provided for September at 4-month lead time, and these were kind of similar to the American-Canadian ones with trends, and rather, I think, a bit larger in the detrended time series. Okay, so we were all rather enthusiastic about this and thought it would be great to submit forecasts to the Sea Ice Outlook. Here's the 2014 August Sea Ice Outlook. So if we had gone ahead and submitted an SIO forecast from our observational system, which we were all keen to do, it would have looked like this. There we are. So clearly this would have been embarrassing to have a bar from the Canadian system going all the way up here with about a plus 500,000 kilometer anomaly relative to 1981 to 2010. And in fact, here was the observed concentration, which was near the high end of the predictions, but still far, far below what the Canadian system would have predicted. So we really had to go back to the drawing board and ask what's going on here. One problem that was identified rather quickly, this is from that initial Sigmund et al. Paper, is that the Hadley version 1 analysis that we used to initialize concentration, this shows trends as a function of calendar month over a period, I believe, 1979 to 2009. And compared to NSIDC, we see that the trends in the Hadley analysis are much too weak, particularly in certain months. And if you take a slightly different view and plot the monthly anomalies over the satellite era, so the Hadley version 1 is in gray here, NSIDC values are in red, and we see that the Hadley values early in the period tend to be lower, later in the period tend to be higher, indicative of the weak trends. And in particular, after about 2002 here, we see that there are no positive anomalies in NSIDC, but all sorts of positive anomalies in the Hadley analysis. So this is an interesting plot. I'll take a few seconds to describe it. So it's a bit similar to the one on the previous slide, except looking now at the period from 2010 to the beginning of 2016. And the black line is the Hadley version 1 anomalies with the 1981 to 2010 climatology subtracted out. And the dashed line is the anomalies of the real-time initial conditions using the Hadley version 1 climatology. So they're indicative of the anomalies in the real-time forecasts. And the red circles are the sea ice extent values for the first month of the forecast, which tend to reflect the initial conditions. And we see that in the hindcast period, these red dots tend to follow the Hadley version 1 values, which are used for initialization. In the operational period, they tend to follow the operational values. So we see a couple of things here. First of all, with these awful positive anomalies in the Hadley time series, and which are implausibly large for this period. And second of all, if we look at the operational period, we see that the dashed line can lie considerably above by up to 1 million square kilometers, the solid line, particularly during the melt season. So the CMC analysis just simply seems to have more ice, particularly in those times of year. So if we might ask, why not just initialize the hindcast with NSIDC, which has better trends? Well, if we look at differences in a particular month, say July 2012 in the melt season, sorry for the blurry plots there. So the difference between the CMC analysis and Hadley version 1 is here. We see mainly positive values reflecting the CMC analysis has more ice. But the difference with the NASA team and NASA Bootstrap are even larger, and I guess the NSIDC time series is a combination of these two. So that would give us better trends, but it wouldn't solve this mismatch between the hindcast and operational sea ice concentrations. So we turned to another possible data source. In 2015, the Hadley version 2 analysis became available. And what it does is applies bias adjustments, which are developed from overlap periods between different data sources. And some of these bias adjustments are based actually on National Ice Center charts, and the intention is to correct for the low bias, particularly in the melt season in passive microwave measurements, which apparently is not as prevalent in the CMC analysis. And this just shows the extent anomalies from OCSAF, which is the basis of passive microwave data for this analysis, the NIC charts, and then the adjusted OCSAF is rather close to the chart climatology. So the top row now shows again for several months differences between the CMC analysis minus the Hadley 1 version, and the bottom is minus the Hadley 2 version. So we see that clearly there is less orange in the bottom row, a better match with the operational initial conditions. But we do see also that there are persistent biases in the Canadian waters. And this is exactly where the CMC analysis assimilates Canadian Ice Service chart data. So these are the regions covered by the CIS charts. And so the approach we took was to, there's a archive of digitized chart data covering the entire hindcast period. And what we did was interpolate this in time and space to the model and merged that with the data set. So we, with the HAD ISST2 data set, and so we call that HAD2 CIS. And we see for this particular month, the high biases in Hadley version 2 are largely mitigated by this merger with the Canadian Ice Service charts. And so the trends now in the HAD2 CIS data look like this, rather similar to the NSIDC trends. These positive anomalies are gone, and with the exception of maybe one anomalous month here. Okay, so those are two of the issues with the initialization that were worked on. And a third is that has to do with the initialization of sea ice thickness in the hindcast. So the problem is, so here's an example for initialization at the beginning of this past May, what this model-based climatology looked like, provided for initial conditions. So it's not awful, but you know, the thicknesses are of the right magnitude, but there's too much ice in the Western Arctic here, not enough above Greenland. And so the approach we took was to develop a statistical model which is trained on biomass and can easily be run in real time. And this is described in a paper by Arlen Dirksen et al. In Journal of Climate. And so what this initial conditions based on the statistical model look like for this past month's forecast is here. So with these three improvements, we've rerun in a complete set of hindcasts for the two models. So these are anomaly correlation skills as a function of lead and season. Now it's sort of those previous diagrams are turned on their side. And so this is for the old initialization and the new initialization. And we can see the much higher skills, even 0.85 or longer for the entire 12 months of the forecast in certain seasons. And as sort of a test, we did submit forecasts to the 2017 Sea Ice Outlook. So this is from the postseason report. We called these modified CANSIPs, and so the June, July, August contributions are shown in the red boxes compared to other dynamical models. And so we see that they were a little bit below the observations, although I think the observations were within the 95% confidence intervals. And if we had submitted the operational predictions, they would have been up here again. They would have been extreme outliers. There were also, and then this was shown by Ed, I believe, and so there were also sea ice probability forecasts submitted, which looked rather reasonable, had one of the lower Briar skill scores, lower being better for all 3 of the months. So based on this proof of concept, we decided to go ahead and target operational implementation of this, this improvement. So the Canadian forecast for the workshop will be split across more than one presentation, but this is for CIS extent. For May, our May forecast has a value of 4.88, which is just above the median. The April one was a bit below the median. Very large, 95% confidence interval based on the ensemble spread. We're sort of going to have to take a look at that. So our forecast is, based on the May prediction, is above the median, but we're going to call it very uncertain due to the closeness to the median, the fact that the April forecast was below, and also this large ensemble spread. Although this value, these values seem to be in the same ballpark as most of the others we've seen. So to summarize, the original initialization gave okay hindcast skill, but terrible real-time forecasts. We identified and made efforts to correct 3 deficiencies in the initialization. So this leads to greatly improved skill and reasonable real-time forecasts finally. And so these changes are being considered for operations. And another interesting change in operations will be the implementation of a new GM-NEMO model, which is based on ORCA-1 and SICE, also nearing operational use, and we'll be excited to see the performance of CICE forecasts in that model as well. Thank you.
Very good questions. Ed?
It's not really a question, just a point of clarity, that the HADIS 1.1, so the HADIS data I showed in mine was HADIS 1.2, which has had these trends kind of sorted out.
Okay, that's good to know. I don't know if that was available when we did our original hindcast, but okay, so there is an intermediate version that addresses some of these issues.
Yeah. I'm presuming that, therefore, from your results, that I don't know this because I don't work on HADIS, but I'm presuming the Canadian iService charts have not been used for the bias correction, because is it just the NIC charts?
Yeah, just the NIC charts.
And,
and I don't know why the Canadian, well, I guess apparently the Canadian charts have more ice in the Canadian waters than the NIC charts, or else the, bias wasn't fully corrected.
Another question, one there.
So if you go back to the your contribution to the CIS outlook before that one, yeah. So you can see that actually the June forecast has a closed value compared to observation. But if you move back forward, you show the, no, go back. Yeah, and you can see actually for 3 months, you have the lowest correlation. When you lead month 3, actually it's just a lower up. Oh, that's different season,
Okay,
I see.
Okay, so centered on September would be this one, lead month 3. So this would be the anomaly correlation skill is somewhere around point.
I'm sorry.
Close to 0.9.
Yeah, I was looking at the different season. I was looking at March, April, May, so I thought it's different, but that's right.
Okay. There's one question here.
Did your skill for the detrended anomaly correlations also improve in this new system?
Yeah, good question. We this is sort of hot off the press, and we haven't computed those based on other things like advanced retreat dates and CIS. It does appear that they're improved, but just didn't have that on hand for the extent.
Okay, thanks.
Okay, thank you very much. So we close the session here. There is any announcements, or we just go for coffee? Coffee.